We're on page 118. This is a take two, unfortunately, the 35-minute video. Oh my god, it didn't record. So hopefully this time it works. But I didn't. I obviously a lot of things I erased, but I left some things, so hopefully it won't be 35 minutes. So differential equation here. So the green picture on the right is explaining what we're doing here. So this is the differential equation, and what we want to solve is for v of t. And the Laplace transform method says translate from the differential equation dE into an algebraic equation AE using the Laplace transform. So you write it not as a function of variable t, but of variable s. The algebra equation is easy to solve, big V of s, and then you take the inverse Laplace transform to go back, and so you've solved the differential equation. What we're going to have to do here is take the Laplace transform of both sides of this differential equation. And so what we're certainly going to need here is some equations from the tables, and they're written down at the bottom in orange. So the dv dt is the first derivative of v, and so we're going to need that formula down the bottom. Now the role of f is going to be played in here by v. So rather than big F, it'll be big V. Rather than little f, it'll be little v. Then we're looking at the constant 9.81. That's going to use the middle rule there. Constant gets sent to constant over s. And then we have, from the green picture, little v of t is sent to big V of s. So let's do that. So we had the first derivative, the dv dt, is going to be sent to, using the first rule, s times big V of s times little v of 0. So that's what dv dt is going to be sent to. Oh, it's tough to write the same thing again. Anyway, stop giving out and just get on with it. So s times big V of s minus little v of 0 equal to 9.81 is a constant, is sent to 9.81 over s, and then minus 0.025 times little v of t is sent to big V of s. So now what we're going to do is apply the initial conditions, which are that the value of the velocity at time equal to 0 is 0. So this little v of 0 is equal to 0. So we get s times big V of s minus 0 is equal to 9.81 divided by s minus 0.025 times big V of s. Now we're trying to solve for big V of s, so what we should do is get all the V of s's on one side, so add that to both sides. So if we do that, on the left hand side we'll have s times big V of s plus 0.025 big V of s equal to 9.81 divided by s. And what we do here is we take out the common factor of V of s. The 9.81 over s. Now the blue stuff on the right is explaining what happens next. So the easy way to explain this is say, oh, you want to get V of s on its own, it's multiplied by s plus 0.025. So divide both sides by s plus 0.025. And the way I would say it, the easiest way to say it, in my opinion, is you got 9.81 divided by s and also divided by s plus 0.025. So I think that's the easiest way to think of it. Now we've got two alternative ways of explaining why, if we divide 9.81 over s, dividing that by s plus 0.025, do we get what we get here. So the first explanation is to literally write 9.81 divided by s, all divided by s plus 0.025. And what you can do then is you can say, oh, I don't like a fraction in a fraction. And if you look at the s on top, so if you multiply above and below by s, multiplying by s on top will it'll undo that division by s. So 9.81 divided by s, now multiplied by s is just 9.81, and you get the s times s plus 0.025. The alternative is to understand that division is multiplying by 1 over. So if you want to divide by s plus 0.025, that's the same as multiplying by 1 over s plus 0.025. And how do you multiply fractions together? Top, top, bottom, bottom. So that's how you get that. So now what we have to do now is, where are we in terms of the green picture? We're down the right hand corner at big V of s. We need to apply the inverse Laplace transform. Now if we look in the tables, you haven't got anything that's exactly like this thing here. So what you want to do is use partial fractions to write this as a sum of simpler terms. Okay, so we're going to take V of s, which is equal to 9.81 divided by s times s plus 0.025. Now the bottom is factorized, that's the first step. And the second step is to look at the rules. Now you've got two rule ones here because you don't have any squaring going on. And if it's all rule ones, you can use the cover-up method. So the partial fractions theory says you're going to have something over s plus something over s plus 0.025. So you're going to have some constants here. And the cover-up method basically gives you a way of finding them pretty much in one line. So what you do is you first recognize when are the things on the bottom, the denominator is equal to 0. So s, almost like a trick question, s is equal to 0 when s is equal to 0. And this is equal to 0 when s is equal to minus 0.025. Now what we do now is we cover up, say for s, you cover, if you want to find the constant for s, you cover up s and put s equal to 0 into everything that's left. So if you look at what's left there, we have 9.81 divided by, so if you cover up the s, you're just left with s plus 0.025. And you substitute in s equal to 0 into that. Then for the other term, you cover up this yoke, and what are you left with? 9.81 over s. So you get 9.81 over s, and you substitute in the value of s that makes the bottom 0. So there's an s at the bottom, substitute in that minus 0.025. These are just numbers you can get in the calculator. They're, I think, 392.4. Maybe I should just double check that. 9.81 divided by 0.025. 392.4, yeah. And the other one, so it's minus 392.4 over s. Now, we might just take a little bit on the side here and just say, if you have, say, for argument's sake, let's say 4/7 plus minus 2 over 5. We're going to have a similar situation here because this number here is negative. So if you've negative over, well, what looks positive, that whole thing is negative. So that's the same, like you can say 4/7 plus minus 2/5. And adding a negative is what subtraction actually is. So in exactly the same way, we can say that because the number on top of the purple bit is minus 392.4, you can get minus 392.4 divided by s plus 0.025. Okay, and now both of these are in the tables. So we're going from big V of s back to little v of t. So a constant over s goes back to the constant 392.4. And then the minus 392.4, you can fix that constant and you're left with 1 over s plus 0.025, which is e to the minus 0.025 t. Okay, and then the next question is what happens to this when time gets big? Now the 392.4 just stays, that's a constant, but the second term, okay, you got this big number, nearly 400, but it's multiplied by something that goes to 0. So what happens as t goes to 0? V gets closer and closer to 392.4. And why is that? as e to the minus 0.025t goes to 0. Negative exponentials go to 0. Now, in context, this is a terminal velocity. It's the velocity that the parachutist will get closer and closer to. Okay, that's an example. Now move on to the next one. Tricky enough question here. So we've got a differential equation. Now the first thing to notice is that it's a function of x rather than t. So we're going to go from x to, we always go to s, but when we come back, it won't be back to t, it'll be back to x. And the other thing to notice is, like, you want to do little theta of x to big theta of s, and we're looking up the top of the page. There is actually a big theta of s, that funny looking face. It's easier, rather than using the big theta, that we'll just write, instead of big theta, we'll write big T. So that's two things, and that's kind of recommended there. So in this one, we're going to again take the Laplace transform both sides. So what's playing the role of f? What's playing the role? Well, we've got the role of t is being played also by x. That's also important. So instead of t, you have x. Instead of f, you've got theta. And if you've got little f going to big F, you're going to have little theta. Here we're going to say big T instead of big theta. And so the relevant formula is in orange here, because we have the second derivative here. We'll be using that orange formula that is in the tables. So looking at the differential equation here, I am going to take the Laplace transform of both sides linearly. So the d2 theta dx squared is the second derivative, minus fix the constant, looking down the bottom of the page now, fix the constant minus 0.1 times Laplace transform theta of x equal to Laplace transform of the minus 0.2. So using the various formulas, so the orange formula will give us, so use the orange formula. So a second derivative gets sent to s squared. Now it should be big F of s. Now you go from little f to big F. Here we're going from little theta. We're not going to use big theta, we're going to use big T. Minus s. Now we don't have little f of 0 here, we have little theta of 0. Minus not f dashed of 0, theta dashed of 0. Okay, so that's the first bit. Then fix the minus 0.01, and then theta of x is going to be sent to big T of s. Equal to, what's the constant going to be sent to? The L of minus 0.2, well, we saw that in the previous page. Constant gets sent to constant over s. So minus 0.2 over s. That's the first step. Second step is to apply the initial conditions. So theta of 0 is 40. So let's go on that. So we get s squared times big T of s minus s times theta of 0 is in the differential equation is 40, minus theta dashed of 0 is 0, minus 0.01 times big T of s equal to minus 0.2 divided by s. Okay, and now what we're going to do is solve for big T of s. Now what we want to do is we want to get this out of there, so we're going to add that to both sides. So if we add that to both sides, we're going to have s squared times big T of s minus 0.01 times big T of s equal to 40s minus 0.2 over s. Now, we have to solve for big T of s. Now, there's a suggested answer given here. We're going to go as far as we can, and then we're going to move a bit towards that. Okay, so what you should do here is take out the common factor of T of s. What are you left with? S squared minus 0.01 equal to 40s divided by 0.2 over s. Now we've got a little comment to make here about if you're dividing a sum by something. So say if you've got, say, 8 plus 22, say, divided by 2 for argument's sake. So that is the same So if you're dividing a sum, you can divide them both separately. You'll find that they're the same thing. So that's going to be relevant here, because I'm going to divide both sides by s squared minus 0.01, and I'm going to divide 40s, and I'm also going to divide the other term. So if I divide both sides by s squared minus 0.01, the multiplication by s squared minus 0.01 on the left hand side is gone. And I got 40s divided by s squared minus 0.01 minus 0.2, which is divided by s, and now also s squared minus 0.1. Okay, so now at this point we'll look at the solution and notice at least that it's written as a single fraction. So if I want to write this thing as a single fraction, I'm going to need a common denominator, and I suggest that we use this common denominator here. So the term on the left, the 40s over s squared minus 0.01, is missing the s, so I can multiply above and below by s. That red thing is equal to 1, so while it makes it look different, it gives it the appropriate denominator, it doesn't actually change the number. So I end up with 40s by s, which is 40s squared, all divided by s times s squared minus 0.01 minus 0.2 divided by s times s squared minus 0.01. And we've got a common denominator, so we can write this as a single fraction. Now if we compare this with the answer, we're nearly there. We've got the top, but the bottom looks a bit different. So what we have to do is factorize the s squared minus 0.01. Now, there's loads of different ways of doing this. So a cheat is to look at the answer and multiply out the bottom, the s minus 0.1 by s plus 0.1. And if you do that, you'll see that the product in the answer is the same as s squared minus 0.01. So the left is equal to the right is equal to the left, so that's a cheat. The other way is all related in various different ways to the fact that we've got a difference of two squares. So s squared, and so the general kind of thing is that s squared minus something can be factorized because it's s squared minus, you can write an omega, in this case the 0.01, as square root of 0.01 squared. So you can see the s squared minus 0.01 as s minus square root of 0.01, s plus the square root of 0.01. We might just write that in here, that the square root of 0.01 is equal to 0.1. That can be compared with something you can't factorize, s squared plus something positive, which you write as s squared plus root omega squared. Another possibility is that you recognize that 0.01 is the square of 0.1 and use difference of squares. And another possibility is that you use the factor theorem, that every root gives you a factor. So if you solve s squared minus 0.01 equal to 0, every root gives you a factor. The two roots of that are plus 0.1 and minus 0.1. And so if you make factors out of that, so the plus 0.01 gives you s minus 0.01 as a factor, and the minus 0.01 gives you s minus minus, in other words, s plus 0.01. And there's various different ways of doing it. However way we do it, we end up with, as expected, t of s is equal to 40s squared minus 0.2 divided by s s times s minus 0.1 times s plus 0.1 as was requested. Okay, so now let's do part B. So part B is that we send back the theta of x. Right. So to find theta of x, we must apply the inverse Laplace transform. So let's write t of s here. So it's 40s squared minus 0.2 divided by s times s minus 0.1 times s plus 0.1. Now the good news here is there's no squares involved. So you're talking rule 1, rule 1, rule 1. And if it's all rule 1s, you can use the cover up method. So we have that the partial fraction theory tells us it's going to be something over s plus something over s minus 0.1 plus something over s plus 0.1, and you can go through it in the you can do, you know, a, b, c, and say that these must be equal and kind of proceed like that. But if it's all rule ones, you can do the cover-up method, which is far easier. Okay, so the cover-up method says, okay, say the constant for s, say when is s equal to 0? That's almost like a trick question. That's for s equal to 0. When is s minus 0.1 equal to 0 for s equal to plus 0.1? And when is s plus 0.1 equal to 0, s equal to minus 0.1. And what you do is you say for s, you will cover up the s. So imagine that's not there. Actually, that would be better. Cover it up as if it isn't there. Yeah, that was better. And substitute in the appropriate value of s in the first case, s equal to 0, into what's left. So here we have 40 s squared minus 0.2 over s minus 0.1 and s plus 0.1. That'll be the first one. If you cover up s minus 0.1, look what you're left with, the 40s squared minus 0.2 over s times s plus 0.1. So what are you left with there? 40 s squared minus 0.2, and you're left with s and s plus 0.1. And then the last one, cover up s plus 0.1 and see what's left and substitute in s equal to minus 0.1 into that. So you'd get 40 times s squared minus 0.2 and s times s minus 0.1. So now you're going to throw in the appropriate values of s. So the first one is what makes the bottom 0? 0. Next one, what makes the bottom 0.1? And the last one, what makes the bottom 0 minus 0.1? And I think it's 20, 10, 10. Yeah, I remember. So if you bang in that into the calculator, that into the calculator, that into the calculator, you will get 20 over s plus 10 over s minus 0.1 plus 10 over s plus 0.1. And these can be easily sent back. Now, so this is big T of s, so big T of s, we go way back, goes back to, well, we're not going to do little t, we're going to do theta of x. So therefore, theta of x goes back to, so constant over s we've seen goes back to the constant. Now, the last term is easy. So you can fix the 10, and 1 over s plus something goes back to negative exponential. Now, the only difference here is you're not going back to t, excuse me, you're going back to x. So it won't be going back to e to the minus 0.1 t, but minus 0.1 x. Now, the other one with the negative, if you basically take the 1 over s plus a form and write a to the minus b, what will happen? Well, you'll have e to the, let me write this again. Maybe we'll just have space to get it right. So you'll have 1 over s plus minus b goes back to inverse Laplace transform e to the minus b t. And of course, first of all, what is s plus minus b? Well, that's just the definition of s minus b. And what's minus minus b? That's plus b. So if you have a 1 over s minus, it'll go to a positive exponential. So here we'll have 10 e to the plus 0.1. Now not t here, but x. Okay. Now usually you won't see these positive exponentials because usually you're working with time. So time will usually be unbounded, so it'll go on to infinity, and the positive exponential will go to infinity. But you don't have infinities really so much in the real world. Where you will have these positive exponentials might be on a beam, so that'll be an x, where you're only interested in so many values. You're not interested in the length of a beam going to infinity, just up to whatever the length of the beam is. If we plot the solution here, by the way, we get this U shape, and that's because the air temperature is 20. It's kind of lowering it a little bit. If the air temperature was bigger than the temperature, bigger than, well, what temperature is it's a bit hard to say, but it would have more of an N shape. Now that only actually went to 26 minutes, so obviously the bits that I didn't rewrite saved us a lot of time. I probably went a bit faster than I would like because I was kind of angry, but you can pause and rewind.